when we say percent yield, tell me what kind of, what other correlations or associations do you have with the word yield? Yeah.
The yield sign.
Okay, sure, the yield sign. Unfortunately, unrelated to our topic today. What other word association do we have with yield?
Kind of give.
Give or produce. Good. That's what yield means in our chemical reactions. The arrow corresponds to what the reaction is yielding, and so that means what it produces. And so when we talk about percent yield, we're essentially figuring out what is our reaction making? How efficient is our reaction? Is it producing what we expected it to produce? Okay, so let's take it into real world for just a second. If you plant 10 sunflower plants, okay? I plant 10 sunflowers, but only 8 grow. Only 8 come up and grow. What's my percent yield, do you think? 80% yield, right? I yielded 80% of what I expected to yield, right? Expected yield is 100% because I planted all 10, 100%, but I only yielded 80. So that's really what we're looking at here, okay? We're going to figure out in a chemical reaction what is our actual yield versus what we were supposed to have. So everything we've been calculating so far out of our T-chart is considered theoretical, okay? Everything we've done so far is theoretical. And theoretical means what? What's theoretical mean?
Hypothetical.
Yeah, hypothetical or what should happen. Okay, theoretical is what we expect, okay? When we actually do the experiment in the lab, we will get what's called an actual yield, right? Which means when we go measure it in the lab on a scale, what our product is, that would be our actual yield. And so to calculate percent yield, we take our actual divided by our theoretical, times 100 to get it into a percent. Okay? What do you think? Are there any ranges for percent yield that we should know about? Could our percent yield ever be over 100? Should our percent yield ever be over 100? Right? Hopefully not. Okay? There could be scenarios where we do have over 100% yield. That could happen if there was some error in the lab in our measurements. It could happen if some of our chemicals were contaminated and there were other minerals or something from the water in there. It could happen if, it didn't get all the way dry. Any of those things could contribute to our percent yield, but that's kind of what we're looking at, okay? So let's go ahead and see this next reaction. For some reason, mine didn't show up very nice up here. Is it nice on your sheet? Okay, great. Okay. So here's my arrow, okay? First of all, tell me what type of chemical reaction is this? C6H6O3 plus O2. Not double displacement, it's combustion. Combustion, because it starts with a hydrocarbon and oxygen gas, and it has carbon dioxide and water as products, right? This is our key for combustion, is that we have CO2 and H2O as products. Okay, that's our key there. Okay. This says how many grams of water will be formed if 36.5 grams of oxygen are used. So this is just a regular stoichiometry problem, right? But then it asks me, what's the percent yield if only 7.95 grams are formed? So this down here would be like we did it in the lab and it's the actual yield. So we're going to hold on to that and save it for a second, right? If my goal is to find the percent yield and I have my actual yield, I need to get my theoretical yield. Okay, I can't have a missing percentage and a missing theoretical yield. I have to find my theoretical yield, and a theoretical yield always comes from a T-chart. Okay, so T and T. Theoretical comes from your T-chart. Okay, let's remember that relationship, okay? So if I want to calculate how many grams of water should be formed, what's my theoretical? That's going to come from my T-chart. So let's start our chart up here. We're going to start with what we know, 36.5 grams of oxygen. When it says oxygen, am I just going to use O? Do I just use O? What do we think? What do you think, Hannah?
O2.
We need to use O2. Tell me why we need to use O2.
Because it's so small that it can't like be by itself.
Right, it does like to have a partner. But, hey, I want you to listen to this. Put your eyes up here. A lot of you do this when you're doing your problems. You just see oxygen and you write oxygen. But anywhere in our reaction, do you just see a regular O?
No.
What do you see?
O2.
O2. Okay, so this is, we got to make sure that we're focusing in here, okay? If it were me, I would go up here and I'd write, we're starting with 36.5 grams, and we want to know how many grams of water we're going to get, right? Help yourself hone in on the two substances you're studying, okay? So I'm going to start with 36.5 grams of O2. Remember, I'm going to walk through right here. So grams of oxygen have to go on the bottom to get rid of it. And what am I going to here? Moles of oxygen. I have to convert from grams to moles. Then I just keep walking through my chart. Moles of O2 has to come down here to keep working because it's not what I want. I don't want moles of O2. I want to get rid of it. And so now I can make the switch to H2O. Right? What's that step of my chart called? Mole ratio. It's called the mole ratio step. Okay? And then last thing here, I don't want moles of H2O. That's not what I want to finish with. I want to get rid of moles of H2O and go to grams of H2O. So now let's come back in and put the numbers. Okay, so let's head back to it and put the numbers in. What value is always going to go with grams? The atomic mass, molar mass, good. Okay, the molar mass goes with grams. So for oxygen, is the molar mass just 16? It is 32. Okay, and what about up here? Do I put the 6 for the O2? I don't. This is where I say 1 mole of oxygen weighs 32 grams because 6 moles of oxygen doesn't weigh 32 grams, right? 1 mole of O2 weighs 32. All right, let's keep going. This is our mole ratio step. And what numbers do we get to put in there? They come from our... Yep, we want 3 for H2O and 6 for O2. They come from our reaction, right? Those are the coefficients from our reaction. Okay. The last step here, molar mass goes with grams. So for water is 18. And then our mole underneath gets a 1. Okay. And so to finish our math, we multiply across the whole top, divide by the whole bottom. Go ahead and run that math and let's see what we get. I want to make sure everyone's plugging that in and can do it correctly. Sophia, what'd you get? 30.8, is that what you said? I had it a little lower than that. Kira, what'd you have?
10.26.
10.26. Caliber, what'd you have?
10.26.
I had 10.26 also. Did you divide by your 6 on the bottom, Sophia? Okay. Oh, okay. No problem. Okay. Everyone else on their calculator, are we coming out correctly here? Okay. So this is 10.26 grams of water. Is this our theoretical yield or our actual yield? Theoretical. It comes from our T-chart. So now we're going to bring it down here and put it into our percent equation. So percent yield is equal to the actual yield over the theoretical yield. So let's go ahead and do that math. 7.95 divided by 10.26. Okay, and I get 0.7748, and it keeps going, whatever. I don't need to write out more numbers than that. But this is not my percentage yet. It's not 0.77%. I have to multiply that by 100. Okay, so my percentage is actually about 77.5%.
look at my chart. Calculator.
Yeah.
Oh, boy.
Say it again. It's the percent yield of water, right? We thought the reaction was going to produce 10.26 grams of water, but it turns out it only produced 7.95. So we lost some of our product along the way. Could have been from error, could have been from like problems measuring, what are they called? Impurities in our substances. All of those things could cause an error in percent yield. But that's kind of what we're looking at. Does that make sense, everybody? It's just like how you calculate your percentage on a test, right? Your theoretical is what you should have gotten, right? A perfect score. And your actual is what you actually got. And you divide that to take it by 100, right? It's the same principle here, just calculating that percentage.
So will you ever get like 100?
You could get 100, right? That would be the case if our theoretical and our actual were exactly the same.
So this just kind of shows how much is correct?
Mm-hmm. Kind of, yeah. All right, let's try another one. If the reaction of 40.8 grams of C6H6O3 produces a 39% yield, how many grams of H2O will be produced? So this is asking a little bit of a different question here. Okay, let's read it one more time. If the reaction of 40.8 grams of starting amount, so that's what we're starting with, produces a 39% yield, how many grams of water will be produced? So that means we only produced 39% of the H2O that we thought we were supposed to. Sorry, I'll get a different color. Right? We only produced 39% of the water that we were supposed to produce. And so it says how many grams of water will be produced. What does that mean our overall goal is to solve for here? The actual yield, exactly, right? We want to find out how many grams of water did we actually produce. So our goal is to find the actual yield. Okay, so we have to work way backwards from this point. Okay, we have to work backwards. If I know my percentage, 39% equals actual over theoretical. This is what I'm solving for, which means I need to find my theoretical yield. And where did we say theoretical yield always comes from? The t-chart. Okay, so now let's go ahead and make a t-chart. Do I start my t-chart with 39%? No, I start with 40.8 grams. And what am I going to? What substance am I going to? H2O, water, right? Because it's asking about percent yield of water. So I'm going to find out how many grams of water should the reaction produce. Okay, so let's start with what we know. 40.8 grams, C6H6O3. And let's walk it through just like we normally do. Sorry, Nathan, do you have a question? Oh, okay. I'm going to give you about a 2-minute head start. I want to see if you can get the T-chart built yourself. And then we'll see if it matches mine here in just a minute or so. Find one?
Yep.
Yours or just one? Okay. Does someone know you took it?
Yeah.
Okay.
I was just giving it in a minute.
Okay. Okay, I've got my units up there if you want to check to make sure your chart is looking similar, right? I'm always leading diagonally. It's telling me what needs to come next, right? If I want to get rid of it, I'm going to put it on the bottom. So let's lead that and figure out what I need to go to. All right, now I'm going to start putting some numbers in. All right, Evan, you got a final answer here? 17.48. Okay. Brooklyn, what'd you have? Perfect. Okay. Is that what you guys had also? 17.48? No? Nathan, what you got? You got what? Okay, fine. Did your molar mass a little bit different?
No.
Okay.
You did it, by
Okay, so tell me this number right here.
There should be one.
This number, you guys keep working on that. You're fine. Keep getting that worked out. This number right here, is this our actual yield or our theoretical yield? Theoretical, because it always comes from our T chart. Remember T and T. So if I'm going to go look at this equation up here, 39% equals actual over theoretical. I have to do a couple things with this equation right here. When we calculate percent, we always take it times 100. In which case, this right here needs to be divided by 100 before we put it in our equation. So 39% really needs to become 0.39 equals actual over theoretical. Okay? Because we multiply it by 100 to get it to a percentage, we need to reverse that before we put a percentage in the equation. So we make that 0.39 equals actual over theoretical. So now what algebra do I need to do to get A by itself? Multiply 17.8 times 0.39, right? I'm multiplying by 17.8 on both sides, and it cancels for me on the right, and it gives me my answer on the left. So 17.48 times 0.39, and I get an actual yield of 6.82 grams of water. Okay, how do we feel about that? Okay, this part here, we can't forget to do this divide by 100 part, right? We don't put percentages into our equation. It's got to be as a decimal. Okay. Tell me what questions or thoughts we had with that. Okay. Why don't you go ahead and try the last one on your own. I want you to try this next one on your own. Okay, so here's our reaction up here. Did your guys' print better than mine? No, it didn't? Oh, it did. Okay, sorry. It's okay. All right. This says if 20.7 grams of calcium carbonate, that has to be this one up here, 20.7 grams of calcium carbonate. I'm going to move this up here. Produces 6.1 grams of calcium oxide. What is the percent yield? So it says it produces this much. This has to be my actual yield, right? Because it's saying it actually does produce that much. So that's my actual yield. We need to find our theoretical yield in order to calculate percent. Okay, so let's go ahead and try this one on your own. I'll be walking around if you need help with your chart, or if you want me to check your chart before you get too far into the math, let me know and I'm happy to do that. Okay? We're going to calcium oxide. You know which one that is? CaO. Right, let's make sure that we're focused on the two correct formulas. So from grams of this to grams of that. If you want me to look over anything on your chart or help you through that, I'm happy to do that. Is our reaction balanced? Did we check that? I think luckily it is. 1 calcium, 1 calcium, 1, 2, 3 oxygens, 3 oxygens. So we're all good to go. Okay, 1 to 1.
How do you go one more, be one more?
Yeah, right. Go ahead and get rid of, let's keep, it's not just Ca, but it's CaCO3, so let's write that whole formula. Good, and then this grams has to go down here. Not the number, just the unit. So let's put the unit down here and we'll go to moles. Okay? And then we calculate molar mass of that way. Okay, if this is correct, which I think it is, I don't know if I'm headed, this would be my theoretical yield because it comes from a T chart, right? That's right. I take my actual divided by that, and that'll come out as a decimal, and then we multiply that. Yeah. Okay, Nathan, is that chart coming okay? Not sure where to go from there. Okay, so we're always going to, if this is grams, which it is, right? Because that's what we started with, grams. I have to cancel it by giving it down. So I have grams of CaCO3, and moles is always my middle name. CaCO3. Okay, so now if I want to get rid of this, where does it need to go? Bottom, right? Okay, so let's keep going from there. And then my switch, the place I want to go is now, this is mole ratio, is now moles of my product. And then I've got to leave with that and then grams. Let's go, a couple more steps. Good. Good, okay, yeah, that's perfect so far. Let's try our molar mass here one more time. Let me see. Okay, let me try this. It's going to be 1 calcium, 1 carbon, and 3 oxygens. The 3 only attaches to the oxygen here. Okay? Did you end up getting that molar mass there? Did that work? So in our calculator, you can go plus 16 times 3. Yep, just like that. Perfect. Okay. Good. Okay. Now we're you're on exactly right track. Let's get rid of moles of CaCO3 and on the bottom. And then you're exactly right now moles of our other. Okay, out of this chart, I think we had a number somewhere around 11 point something. What was that? 11.6. Okay, so this value, because it comes from our T chart, is theoretical. Okay, that's theoretical. Is that different than what you had, Hannah?
Yeah.
A little bit. Is your molar masses the same?
Oh, I flipped it.
Okay.
I did the CaO first.
Okay. All right, this is theoretical. My actual is 6.1, so to calculate percent, I would take 6.81 grams divided by 11.6 grams, and then I would need to multiply that by 100 to get it to a percent. And that gives me about somewhere in the range of 58.7%, right? Depending on where you rounded, depending on how you finish that out, we're somewhere in that range. Okay? Does that feel comfortable?